a virtual and semi-interactive depiction of a cricket match occurring at this national stadium in Guyana. I'll now hand you over to my other colleague.
Okay, so we did our modeling externally in Blender. Therefore, we needed a way to read that data into our project. Hence why we have the model importer, which utilizes a simple helper library, asym, which provides a agnostic way of reading file data from multiple file format structures. So on the left here, we're going to see asym's data structure. So it's just a graph really with some tree-like structures, which most of us should be familiar with. And on the right, we'll see some code. The first box is simply a partial snippet showing how we recursively loop through and read model data. The second here shows what happens in the process mesh function, whereby we're just simply reading and storing vertices. And we can, of course, just store text UVs, normals, etc. So next up, we're going to talk about calculating the geometry of the plane that acted as the ground. So we utilize drawing a circle rather than importing it for two reasons. One, so that we can change the size and dimensions easily. Two, it serves as an anchor for placing models in the scene. So instead of translating models to specific positions, we instead use the vertices on the circle as anchor points. So I could just say add a model and move it to vertex position 0 on the circle. So, and on the right, we'll see the code implementation for this, whereby we're just utilizing the parametric equation of a circle. So you can see how we're calculating this point here. We're actually just doing that here for the X and C components, or the number of sections within the circle. And with that, I'll pass you on to my colleague, Renata.
Blink fong lighting was used in the project for the purpose of contributing effective lighting for the sun and stadium lights, where the main focus in calculation was in specular lighting, and we can see how the stadium is lit up in the image when it's used. The diagrams show exactly how the relationship between the light source, normal reflection vector, view vector, highlight how the reflection is perceived from different perspectives. Another concept which is incorporated into is the halfway vector instead of just using the reflection vector, and this essentially lies between the view and light directions. It was used to resolve issues where the angle of the viewer and that of the reflected is greater than 90 degrees. Other concepts of lighting, such as ambient, diffuse, and specular lighting, were used along with the halfway vector to place these into effect. The halfway vector adds the light and view direction vectors, where the result is then normalized. And we can see the use of the diffuse and specular lighting in our stadium light when it is turned on. Multiple lights which surround the field of the stadium were necessary. Ambient, diffuse, and specular lighting are combined, influenced by the object's color. Next, 4 lights are created by iterating and altering their position in the field once the spotlight is on. And now I'll hand you over to my next colleague.
Okay, so now I'm going to talk about shadow mapping, which was used to add realism to the scene by introducing shadows. So this is a simple and efficient algorithm for rendering shadows in one scene. So the high-level overview of the process is that we first render the scene from the light's perspective and store that in a frame buffer. Then we use that information in the second render pass to check if a candidate is in shadow or not. If it is not seen from the light's perspective, that means it is in shadow. So as I said before, we use a frame buffer to store the depth information. You can see the code for that over here. And then we prepare to render from the light's perspective. And we use the orthographic projection here because we don't want to deform the scene with perspective. And lastly, the shadow will be 1, as you can see in highlighted red blocks there, if the current depth of the candidate is greater than the closest depth value on the shadow map. And you can see that line here. And all the other stuff with PCF and biases are just to help smooth out jaggies and create smoother shadows. So next thing I want to talk about is alpha testing and instancing, which was used to create the grass in our scene. So alpha testing is just a technique to remove transparency in an image, and instancing just allows for the rendering in batches rather than singles. So here you can see the alpha fragment shader, whereby we're simply checking if the textile value is less than 0.5, and if so, we discard it. And then for drawing one grass, since we're just doing this once, we need to create a single flat plane, we need to duplicate and rotate the grass several times per position in order to create the effective result, or so that we can walk around, we're not just going to see a line. And then using instancing was simply relatively straightforward. We simply pre-compute the model matrices, store those in VBO, VAOs, etc. Typical drawing process. But instead of calling GL draw elements, we call GL draw elements instance so that we can render in batches. Next up, we have cube maps. So this is a pretty straightforward concept, and we use this to draw the sky. So essentially, we're just texturing each side of a cube. Two things to take note of is, one, we don't want the sky to move, so we remove translation from the view matrix. And two, when setting up the textures, we use GeoTexture 2D instead of, we use GeoTexture CubeMap, instead of GeoTexture 2D, because we're dealing with a CubeMap. And with that, I will pass you on to my colleague who will talk about skeletal animation.
Now, why did we implement skeletal animation? Simply because seeing all the players and crowd members move brings the scene to life and immerses you a bit more. Now, there are a few concepts needed to implement skeletal animation. The first one we'll be talking about is interpolation. Very basically, it's how an object moves from one keyframe to another. It calculates the intermediate position and rotations, as well as other attributes to create smooth transitions, preventing us from having a sudden jump from one location to another. There are three more components for an animated model: the skin, which is simply the model's meshes; the bones, which are used to move the mesh around realistically due to their hierarchy; and keyframes, which are then interpolated between. Keyframes are made by manipulating the object's positions or rotations at certain intervals. Then we interpolate between them to produce a smooth and fluid animation. And to the right, we can see the final product, where we have multiple complex animation for crowd members. Now, Shivesh will take you through the next concept.
Okay, so lastly, we have collision detection and response. This is just simply prevented the viewer from going out of bounds or falling through the platform. And we use a standard axis aligned bounding box setup. To generate the bounding box, we use data when processing the mesh. We simply check for the leftmost, rightmost, etc. point and use that to draw the box. For collision detection, we use the standard A/B collision detection algorithm, which you can see over there. And for the response, the viewer simply stopped it if its future position would result in a collision. So next up, we have challenges. Of course, there were many, but these are just some that stood out. So reading models data and rendering lots of primitive like the grass lowered our FPS dramatically. We already talked about instant and how that's helped with rendering the grass. But for read and models data, switch rules simply to read that in before the while loop and store it in an array. So then we could just draw it with each iteration of the while loop rather than having to read the data from the models every time. Second, we have suboptimal results for a scene being produced for the stadium lights. So to alter this, we introduced a constant value to increase the intensity of the stadium lights because we wanted them to be brighter. Next, we have errors in debugging. To help with this, we had utility functions that were created, such as one for visualizing the collision box for A/B, and as well as one for visualizing what the scene looks from the light's perspective for debugging and getting the right settings for our shadows. Limitation, these are things that we quite couldn't get over. Of course, there's a time constraint. So as we progressed through the project and we noticed things were designed in like a suboptimal way, but of course refactoring takes a lot of time. So we just kind of had to prioritize requirements and move forward. Two difficulties we maintain output across various platforms. So different people working on different devices. We had people working on Linux and Windows devices. So we had nuances between the output, and no definitive solution was really possible given the time constraint. So we ignored minor changes, and if there were major things, we focused on them. But for the most part, we just ignored what we could fix, kind of moved forward and tried to create the best output. Okay, so here we have our code demonstration. As you can see, here's our scene. We can change animations using a key binding. We can turn the lights on and off, well, the stadium lights at least. And we can see the various concepts we talked about. Here's the rendered grass. You can see shadows over there. There's collision detection to prevent me from going off there. You can see the skybox in the background, and it's always stays the same distance away. And you can see all the various models that were imported using our model importer. There's also the ground that's rendered using the parametric equation of a circle. And yeah, that's about it. Here's the pan around of the scene, and that should be about it. And with that, we come to the end of our presentation. In summary, these are the major graphics related concepts implemented.